Higher Notes, Unit 2, Section 3, Wave-Particle Duality. This is part 2, where we look at photocurrent and factors affecting it. Well, so far we've investigated the photoelectric effect, but we've concentrated on individual electrons being photo-emitted. If you allow the photoelectric effect to take place, then there will be a stream of photons arriving from the incident light, or indeed other wavelengths of electromagnetic radiation, which also cause the effect. And therefore there will be a stream of photoelectrons emitted. And if you have a stream of photoelectrons emitted, you have a photocurrent. So we're now going to investigate how we can measure the photocurrent and look at factors affecting it. Well, the first thing is that when photoelectrons are emitted, if they are emitted into air, then they will be absorbed by the air, so you won't really have much current to talk about. So in order to conduct experiments on the photoelectric effect, the whole thing needs to take place within a vacuum. So here's a typical experimental setup. We very often have a quartz window, which I'm drawing in yellow here. And the quartz window is there because ultraviolet radiation, which does cause the photoelectric effect, as you know, with zinc, can't penetrate ordinary glass. So we have a evacuated glass tube, something like this. And the incident radiation then can come down like this. Okay. And this, of course, is the quartz window. Now inside here we have, let's make it a zinc cathode, but like the one you have seen in the lab with ultraviolet light. And we'll connect that cathode up to the negative terminal of a power supply. That will be a DC supply. There will be another terminal, electrode I should say, which will not be made of zinc. I'm going to put a milliammeter in there. The currents that we measure are quite small. And there we have the setup. So this is a zinc cathode, which is clearly negative in charge. This is an evacuated glass tube. Evacuated means it's a vacuum inside, no air. And this, of course, is the anode. This is the cathode. So, when an electron is emitted, it's going to be attracted across to the anode, because the anode, of course, is positive. And there's no air to absorb it, so it will reach that anode, assuming it's been photo-emitted, and flow through the circuit. And as lots of these electrons flow one after the other, we will register a photocurrent in the ammeter. So we'll show in here the photocurrent I. Right. Now when we do experiments with this apparatus, we get interesting results. The first variation of the photocurrent occurs with frequency. So frequency of incident radiation, that is, so the frequency of the incoming photons. And here's the current or photocurrent in milliamps. And what you find is that if the frequency is too low, you don't get any emission taking place at all, because the frequency of the photon is too low, therefore the energy of the photon is too small to liberate an electron. So the photon energy is less than the work function, and you don't get any photocurrent. But then if you gradually increase the frequency of the incident photons, you get to the point where the frequency is high enough and photo emission begins and the photocurrent begins to flow. And when that happens, you get a graph which curves like that, and that is F0, the threshold frequency. And this interval here there is no photo emission. And the reason for that, of course, is using our Planck equation. That's a constant. If that's very low, that's very low, not enough to overcome the work function. So higher frequency means greater photocurrent. It's not a linear relationship, so doubling the frequency doesn't double the photocurrent, but it is an increasing relationship. So increasing the frequency does indeed increase the photocurrent. Now the second key relationship that we can discover with this apparatus is the effect of photocurrent on what's called irradiance. Now irradiance we will study in more detail later. How should we think of irradiance? Well, very crudely, it's a little bit like brightness, right? But don't ever call it brightness. It's actually better thought of as the number of photons arriving per square meter per second. Okay, so loads of photons per square meter per second, lots of irradiance. The light source would be bright if it were visible. Low irradiance, few photons per square meter per second arriving. And what we find with irradiance is that we get a nice linear relationship. So it's a straight line relationship. Double the irradiance, double the photocurrent. That shouldn't be a great surprise, because if you have let's say 1 square centimetre of zinc to receive the ultraviolet light, and you've got a certain number of photons arriving per second, each photon causes a photoelectron. So if you double the number of photons in that little square centimetre per second, you double the number of photoelectrons. And if you double the number of photoelectrons per second, you're doubling the current, because current is just the number of coulombs of electrons per second, if you like. Okay. A couple of observations. If we go back to our root equation, photon energy is hf naught plus a half m v squared. If we imagine then, if we increase the frequency, let me rewrite that actually, as hf is hf naught plus a half m v squared. If we increase the frequency of the incoming photons, then we're increasing the energy of the incoming photons. Now, Planck's constant is obviously a constant. The threshold frequency is a constant for a given metal. The mass of the electron is obviously constant for a given metal. So you can see that if we increase the frequency of the photons, we're going to ultimately increase the maximum velocity of the photoelectrons. So increased frequency of photon coming in, increased velocity of photoelectrons. And you can see why that's going to give you an increased current, because if the photoelectrons are flying off this cathode more quickly, then more of them per second are going to reach the anode, so you're going to get a bigger current. And there we are. And the fact that it's a v squared term is responsible for that curve. Okay, what about the irradiance? Well, if we increase the irradiance, looking at our equation, all that does is it increases the number of photons arriving. This equation describes the situation for a single photon. Worth remembering that, one photon and therefore one photoelectron. So increasing the irradiance just means this happens more times per second, per square meter. Okay, so the current's definitely going to go up, but increasing the irradiance does not increase the kinetic energy of each individual photon, because each individual photon's kinetic energy depends on the energy of the individual photon coming in. So increasing the irradiance increases the photocurrent but not the velocity of the electrons. Finally, a couple of words on applications. My first point is see course booklet for details. Too much to write down here, but there are several applications of the photoelectric effect. One is in a photo multiplier tube. They are used in various detectors, for example, gamma cameras use them in hospitals. You can read more about that in the course booklet. Charged, or charge I should say, coupled devices, CCDs. These are semiconductor devices, and they're sensitive to light, and they can be used in all sorts of situations. For example, in a digital camera, where the charged coupled device replaces the film, and there is an array of little pixels which detect the light, so they're very, very small pixels, and photons interact with them. So you can again read more about that in the course booklet. There is a light meter in photography, obviously detecting visible light, photons there. There is something called an image intensifier, an optoelectronic device. It takes low levels of light and gives you a much bigger signal, and it uses the photoelectric effect. Again, more details on in the booklet. Right, well that brings us to the end of the wave-particle duality section. Obviously it's very important for you to do lots of problems in this area as well.